Okay, so I guess up to now we're working at a pretty abstract level of talking about environments and policies and what learnability means in general. And then the plan is to, I guess, for today and next week to make things a bit more concrete and look at some sort of simple, interesting cases and see how things play out in these more concrete settings. The topic for today is going to be arguably the kind of simplest possible setting to talk about learnability, which is a setting called bandits. This is like arguably the simplest possible instance of that we can look at. So I guess the simplification is that we assume that so we had this general notion of an environment, which let me just talk about Bernoulli bandits first. They're even the simplest within the simplest. So for Bernoulli bandits, we assume that the observations are just 0 and 1 and considered as a subset of the real numbers. So this being a subset just means that, or here we use this to specify the reward corresponding to that observation. So basically, you can think of it as the only thing we observe is the reward that we receive, and it's either 0 or 1. And let's assume A is finite. And then so we had this general notion of an environment. Equals star. And so here, as I mentioned in the first lecture, sometimes it's kind of more natural to talk about the environment starting and sometimes the agent starting. So for bandits, it's actually kind of more reasonable to think of the agent starting. So we're going to stick an extra action here. So the agent makes the first move. So a general environment eta would be a partial map like this. And we say that it's a bandit if what the environment does only depends on the last action. So that just means that we can factor this as projecting down to the last action. This way. And then that last action determines what the environment does. So I'll write this as there's a function eta a like this, which basically just for each action, it gives us a distribution over the rewards, which in this case is just 0, 1. So I guess the reason these are called bandits, maybe it's not clear if you haven't seen this term, is like you can think of the one-armed bandit that you see in casinos, which looks something like this, where there are like these wheels that spin, and you might get some. You put in some cash for each turn, and then you like pull the arm, and you might get something back, or you might not. And then I guess these are sometimes called multi-arm or many-arm bandits. So you can think of like instead of there just being one arm, there's like multiple levers that you can pull, one for each. So these are the different actions, or these are also called arms in the case of bandits, given this kind of analogy. And then I guess the idea here is that different arms might behave differently. So the task is to figure out which arm is the best one to pull. The little r here, it just means that this is the reward function. So as you saw earlier, the simplest way to specify a reward is just as a map from O to R. And I guess we just take this inclusion as that map. So it's basically, it just means we observe the reward. I think that's the simplest way to think about it.
Yeah, good.
Okay, so those are bandits, or those are Bernoulli bandits. And then I guess more generally, if we just assume the observations are a subset of the real numbers, these would be bandits in more general. I guess maybe I should say for Bernoulli bandits, they specify a certain hypothesis class of environments, which we can write as HBB. So these are characterized by these functions that assign to each arm a certain distribution of rewards. And then more generally, instead of just taking the reward to be 0, 1, we can take any subset, or we could even take the whole real numbers as possible sets of observations. And yeah, so I guess in practice, we might want to restrict what sort of distributions we allow here, but maybe I'll just come back to it when it becomes relevant. Yeah, any questions about this definition of a bandit?
Yeah, eta here you said it's a partial function, but from the weight factors, doesn't it mean that it's always defined?
Yeah, I think in this case it's always defined.
Thank you.
Yeah, I guess it's always defined because we assume it doesn't depend on any of the observations, and that was the only restriction for it being partial. So in this case, it's yeah, it can be taken to be always defined. Okay. So yeah, I guess the plan for today is to consider specific sort of approach for bandits. It's actually, even though they're very simple, there's a lot that can be said about them. They're like all books written about just bandits, but we'll try to do like a kind of gentle introduction. So actually, as a warm-up, I think it's interesting to consider the case where the bandit is deterministic. So this means that our hypothesis class is deterministic bandits. These are just given by this eta A, which for each arm assigns. And so here, instead of a distribution, because we're assuming it's just deterministic, it just deterministically outputs a certain observation, which is our reward. So these are fairly clear, like what the kind of best strategy for learning it. So we can write down a learning algorithm. It's basically, it consists of 2 steps. One is to just try each arm once. Remember, arm is the same as action here. So we try each arm once, and then once we try them, we see which one is the best one, and then basically keep, afterwards, just keep pulling the best, or one of the best arms. Maybe I should say a best term. Maybe there's not a unique one. So yeah, in this case, it's fairly clear that this is sort of the best we can do. We have to try each arm once at least to make sure that we're not missing anything. But because it's deterministic, it's enough to try it once, and then we know what the corresponding reward is. So once we figured out which one is best arm, we can just keep pulling that one. So I guess to write this down formally, we have this algorithm pi, and it's a deterministic one, so it takes a sequence of observations and outputs an action, and it's defined in a way that it maps. We take a sequence of observations O0, O1 to O, say t minus 1. And the output action is, it will depend on if t is less or equal to the size of A, then we just output t, where we can think of, assuming A is just given by 0, 1, 2, size of A minus 1. So here this is just saying, okay, try to arm 0, arm 1, arm 2. And then afterwards, choose I guess the argmax, something in the argmax of the first t observations. Yeah. Any questions about this?
Okay, and so the idea is that for a single environment, there is actually a slightly better algorithm, which is
right.
just pull the arm, which is the best arm.
Right.
But in the limit, your average reward is actually convergence. So it's okay. Is that the
Yeah, exactly. So I guess because we have like a hypothesis class, so we take all deterministic bandits here. So we given all of these hypotheses, for any individual one there is a best term, but we don't know which one we're facing. So given that ambiguity or uncertainty, in order to learn the entire hypothesis class, we do need to try all of the arms. And then, as you said, for any specific environment or hypothesis, it'll be slightly suboptimal because we're wasting the few first term, like playing each arms. But yeah, in the long run, the average regret goes to 0 for all of the hypotheses. So it is a learning algorithm. And in fact, I guess we can identify the regrets of this policy for any deterministic bandits up to time t. We see that it's actually less or equal than I guess we can say it's the size of A, just the number of expiration times. Maybe I should say this will come up later, so it's probably worth writing it out. It's the sum of these gaps where the delta A for a given environment is the reward for the optimal arm. So it's I guess write it as eta star A minus the current arm. That's basically just saying how much worse is the arm A compared to the optimal one. So in the first phase where we pull each arm once, we might might accumulate a regret of this gap for each of those arms. But then afterwards, the regret is 0, and then we take I guess we take the average over t. This. So this is this will go to 0 as t goes to infinity for any environment, which is what Lofkush was pointing out. So this is indeed a learning algorithm for this hypothesis class. Any questions about this?
And I guess we can construct just like infinitely many policies by just doing a finite bunch of random stuff at the start.
Right, yeah. So in general, like learning policies are often, somewhat flexible in that you can basically, if you choose to, you can waste your time in the beginning because sort of the asymptotic behavior is what typically determines learnability. I mean, that's assuming the hypothesis class is sort of forgiving in that you can recover from mistakes in the beginning, which is the case for bandits because they don't have any memory of what you did in the beginning. So for bandits, you can, if you eventually figure out the right thing to do, then you're good to go as a learning algorithm. But if you're trying to minimize the regret, then it's still like kind of worth trying to be as optimal as possible within the ambiguity of the hypothesis class. Okay, so I guess we take this learning algorithm as an inspiration, and if you notice, there's sort of two phases of this algorithm. One is what might be called exploration, where we explore the different actions or the different arms, and the second part is, I guess it's like a commitment, where you commit to a certain arm, or sometimes it's called exploitation. So there are these two phases. And I guess this is one general approach to learning algorithms in general. You can, like this sort of approach can work fairly generally. To first do like an exploration phase and then do an exploitation phase, and I guess some of the nuances and finding the right balance of these two. So kind of inspired by this, we can write down a more general algorithm, which is called explore, then commit, shorten etc. And I'm going to put m here, where m is sort of the parameter that controls how much time you spend exploring. So this algorithm is, I guess maybe before writing down the algorithm, I should write down the definition, which is the definition of empirical average. So we want to define this empirical average mu hat of an arm A, let's say up to time t. So you can think of this as a function that takes in a sequence of actions and rewards, which are observations. And because we want to average over t time steps here, we assume this is a sequence of length at least t, and outputs a real number. So again, we're assuming O is a subset of R. So what is this empirical average? I guess it's intuitively clear what it does, but let me write it down formally. So let's say we take a sequence here, A0, O0, A1, O1, and so on. And what it maps to is, so it's the average up to time t, so it's 1 over t times the sum. And then we can put the indicator function that we pulled arm t or arm a at time t. So this is the sum over different times. T equals 0 to t minus 1. So these are, we pick out the times when we chose action A, and then multiply that by the observed reward at that time. So this should not be t.
The average, yeah.
Yeah, yeah. This should be, I guess I call it C sub A of t, where C sub A of t is the count, the count of arm A up to time t. So these are just, this is the sum of just the indicator function of at equals A. So this is just counting how many times did you pull arm A, and then that way this is actually the average of that specific arm. Okay, does this definition make sense? Okay. So then, yeah, with this definition, we can write down an analog of what we did for the deterministically bandits. So we can define explore then commit sub m. This is a policy, so it takes the sequence of actions and observations up to now, and that puts in the action. It's a deterministic policy. And the way it's defined formally, maybe I should say it informally first. Informally, basically what we do is we pull each arm m times, so that's what the little m is here for. It's the number of times we explore each arm. So we pull each arm m times, and then afterwards commit to the arm with the highest empirical average up to that point, up to the that we got in the exploration phase. So the way it's defined is that we take a history in here, H, and then map it to. So in the exploration phase, we I guess I write it as the length of H. So this is like, I guess, the time mod A, and I guess let's say A is the size of curly A, just for easier notation. So this is basically just cycles through each arm using this mod A, and then so we do this if we're in the first m times A time steps. So that's to cover each of the A arms m times, and then afterwards. Afterwards, we take an argmax of the different arms of the empirical average of that arm up to the expiration time. So this is when we're past the expiration phase of, I guess, knowledge. So yeah, again, this is just formally saying, I guess, yeah, again, we just identify A with the numbers up to a minus 1. So this is a meaningful thing that picks out an action, goes through each term, cycles through each term m times, and then afterwards we just commit to the empirically best term up to that point. Does this algorithm make sense?
One tiny detail.
Yeah.
Do we need to feed it the previous actions? So you put sequences of actions and observations. Can we get away with just the observations in this special?
Yeah. So yeah, that's a good point. So yeah, I guess we talked about. Yeah, maybe we can do an aside here about this. Like a deterministic policy technically would be defined just as a map from here to here, and it's because the past actions are determined. So there's actually not much harm in including the actions as well. It just needs, yeah. I guess it needs to be kind of, yeah, technically we can define this as a partial map where it's only defined on the actions which were consistent with the policy so far. I guess the reason I included it here is not technically necessary, but the way we define this empirical average, it was making use of what the actions were, so it's just easier to write it down.
But if you define it on the trajectory consisting on both of actions and sequences, then you need to think about it as a list of pairs, because you are using the size of H in the definition.
Yeah,
right.
By size of H, I mean the length of the word, so it's like
yeah.
Okay, so hopefully this clarifies that issue. Any other questions? All right. So this is an algorithm, and then the thing we're going to try to do is to show that this can work as a learning algorithm for certain nice classes of stochastic bandits. Because we saw, I guess, maybe one thing to point out is that we saw that ETC1, so where we just explore each term once, learns the hypothesis class of deterministic bandits. And then we want to see that we can choose M carefully enough, and then that will depend on the time horizon. So maybe I could write goal choose M depending on T carefully to get a good regret bound for, let's say, the class of all Bernoulli bandits, which are, I guess, the simplest case of stochastic bandits. So this will be the kind of goal for the rest of today, is to sort of understand how ETC
Why does this
behaves.
depend on T?
Sorry, why does it depend on T?
Mhm.
Yeah, so I guess that's one thing we'll see, and that's maybe one of the shortcomings of ETC, is that basically if you fix an M, then you cannot expect to learn for all of eternity, because no matter how long you explore, there's still a little bit of a chance that you picked the wrong arm. So you cannot just run that algorithm all the way up to infinity. So in general, what will happen is that, we'll take pi sub t to be ETC of m of t, where we allow to vary m depending on the t, and then we want to show maybe that this family learns this hypothesis class. So in particular, this is not going to be an anytime learning algorithm. And yeah, I guess one of the optional homework exercises is to turn this into an anytime learning algorithm. So that's one thing you can try to explore in the homework. And then I think the plan for next week is, or part of the plan is to talk a little bit about the sort of shortcomings or drawbacks of this algorithm, and try to point at in what ways it could be improved. And that's definitely one way it could be improved, is that it really like relies on knowing the time horizon in advance. Does that answer the question?
Mhm.
Okay, so maybe one thing I should mention is that for simplicity, I've been referring to this class of Bernoulli bandits. But actually, like, because this is sort of a very simple case, but maybe it's worth mentioning that we could upgrade this class to a different class called one sub-Gaussian bandits, which I write as one SG. So these are one sub-Gaussian. So I'm not going to talk much about this right now, because I think it's like it's a much greater generality, but it gets a little technical, and I think there's not that much point in going into the technicalities. But basically, basically, if you look at the distribution of rewards, you might get some distribution of rewards for a certain arm. Like if the tail of the distribution is kind of very heavy, that makes it harder to learn, because you cannot like rely on the averages to make good estimates about how good that arm is. So basically, this is sort of just a technical condition to rule out heavy tails. That would be a sort of hand-wavy heuristic for what it is. But I think
so that's basically mean that the distribution of rewards for each arm in this bandit has tails that are at most as thick as a normal distribution.
Yeah, I think basically that's what it was.
Okay.
Yeah. And I wrote down the formal definition in the notes, so you can, if you're interested, you can check it. But I think for the lecture today, we'll just stick to Bernoulli bandits, and just for conceptual simplicity. Okay, so yeah, let's try to understand the regret of ETCM. Okay, so let's look at the regret up to time t of ETCM against a fixed banded eta. So because the algorithm has two phases, the exploration phase and the exploitation or committed phase, we can also break down the regret into those two parts. So in the exploration phase, we pull each arm m times. Yeah, I guess there's a, let me write t times the regret because we define the regret as average regret. So t times it will be the total regret. So here we pull each arm m times, and then so each time we pull an arm, the regret we suffer is this or the, I guess the expected regret we suffer is this suboptimality gap for each arm. But I guess the regret already has the expectations in there. And then, so this is the regret we get for the expiration phase.
What is delta A?
Oh yeah, so delta A. Okay, so for given eta, I guess we can write mu star for the best expected value of any of the arms. And then delta A is basically how suboptimal arm A is. So it's going to be the expected reward of arm A. Delta A is the optimal expected reward minus the expected reward of the specific arm. And this is called the suboptimality gap. This is saying how much worse is this arm compared to the optimal arm. So that way, when we pull an arm A in the explore phase, this is the regret we suffer because this is how much worse we are off compared to pulling the optimal arm for that specific bandit instance.
And so for the Bernoulli bandit, this is just the difference in the probability of one.
Yeah, exactly. For Bernoulli bandits, these expected values are exactly just the probability of one. Yeah, but I guess I'm writing these in a little bit more generality. But probably the notation wouldn't be much simpler for Bernoulli bandits anyway. Okay, so this is the regret we get in the exploration phase. And in the exploitation phase, we commit to an arm and we pull that arm for the rest of the phase. So we pull it t minus m times a times. And then the regret we suffer here is, I guess one way to write it is a sum. This is assuming we commit to an arm A. The regret we suffer each time we pull that arm is the suboptimality gap. And then this gets multiplied by the probability that we committed to that arm. So I write this as committed right. So for each arm, there's a certain probability that we commit to that arm given the algorithm. And then if we commit to arm A, then each time we pull it, we suffer this delta A regret. And because we commit for the rest of the time horizon, we get that regret t minus ma times. Does this decomposition make sense?
Yeah.
Okay, so I guess maybe the most ambiguous thing here is the thing to figure out is what is this probability of committing to a certain arm. So let's try to kind of work it out. I guess yeah, for simplicity, we can assume arm 0 is optimal without loss of generality. Okay, so what is the probability that we commit to arm A? So we commit to arm A if the empirical average of arm A was the best out of all the arms. So this is the probability that mu hat, the empirical average of arm A, after the m times a steps of exploration is bigger or equal to any of the other arms. So this is max B not equals to A of E hat B. And I guess technically this is like, we use this argmax to pick out the best arm, and maybe we pick the first one in the order. So this is like not quite equal, but like we can definitely say it's less or equal than this. Okay, so we have this, and then we can also bound this by saying that this is definitely less or equal than the probability that the average observed for arm A is bigger or equal than the average for the optimal arm, which we assume is 0. Okay, and then so we can rewrite this a little bit. We can say that this is the same as saying that this is the probability of, and we look at how far is the empirical average from the actual mean of the arm. I guess let's write mu sub A for the expected value or the mean of arm A. And then minus how far is the empirical average of arm A from the mean of arm, or arm 0 of mean of arm 0. And then this is saying that this is bigger equal than the suboptimality gap of arm A, which is the difference between the this is mu 0 minus mu A. So this is just rewriting this inequality, but in a way that's a little more parsable. But the reason for rewriting it this way is that this is these two things are, the empirical average minus the mean, and then I guess this was the reason why we restrict to like certain, or we introduce this condition of sub-Gaussian being sub-Gaussian, which was for Bernoulli ones in particular, is just to say that these are so for these certain like nice enough distributions, the empirical average is with high probability pretty close to the mean. So I'm gonna I'm not gonna write out an exact answer. Yeah.
Why is the first line an inequality?
So this is almost an equality. It's just because there might
be.
be like multiple arms with the same empirical average, and then the argmax picks out one of them, which is like maybe the first in the index, and then so because of that, it's like not exactly an equality, but in spirit you can say that it's almost an equality. Okay, so this I'm just going to write down. It turns out that this is less or equal than e to the minus, and then there's an m times delta a squared over 4. So this is it basically comes from something called a Chernoff bound. Oops. Chernoff bound. I added this in the notes as well, but I don't want to go into it here. But basically, it's a bound that says like, okay, these averages are unlikely to be far from their means, and therefore this is unlikely to be big, and then that unlikely can be quantified by this exponential using the Chernoff bound. Okay, so this is basically saying depending on m and delta a, if m is large enough, we're basically pretty unlikely to commit to a suboptimal arm. So that's sort of what it's saying here. Okay. Any questions about this? Okay, so now let's take this estimate that we worked out here, sort of modulo we skipped over the technical part. Let's try to plug it back into this decomposition of the regret and see what we end up with. And to keep things even more simple, let's assume we only have 2 actions, so 2 arms. And so in that case, there's only one suboptimality gap that's interesting, the delta 1, and we'll just write write delta for delta 1, so that we don't carry the index. So with this, looking back here, we have this expiration. I guess I should say is the exploitation. So the expiration regret is just m times delta in this case. And then the exploitation regret, which is this much. So we can bound, you can just write t here, assuming that the expiration time is fairly small, and then plug in the rest of what we had here. So plus t times delta times this bound e to the minus m delta squared over 4. So that's sort of an estimate we can put on the regret. So I guess this is t times the regret, and then the regret itself is 1 over t in all of this. Okay, and then yeah, so we're running a little short on time, so if you try to see, okay, when is the left hand side minimized? You can take a derivative with respect to m, and you get that it's minimized when m is roughly, and then either it's like between 1 or the other thing that you get is 4 over delta squared log t delta squared over 4. Maybe take the ceiling of this. So turns out this is minimized for this choice of m, and if you then plug that back into this bound on the regret that we get that there's a bit of work here to work this out. We actually end up getting that the regret up to time t is bounded by delta over t plus some constant c times the square root of t. So yeah, this is quite nice. This is our kind of first interesting regret bound that we derived in this course. So we see that it has a part that depends on the suboptimality gap, but it goes down with as 1 over t with the time horizon. And then we have this other part other part that doesn't depend on the suboptimality gap, but only decreases with the square root of t, or 1 over square root of t. But we see that this, in fact, it converges to 0 for t going to infinity. So we see that this choice of m, with this choice of m, we actually do end up with a learning algorithm for Bernoulli or one subcassion bandits. So yeah, I think this is our first learning algorithm for which we actually had to do some work to show that it works, and it has an interesting regret band. Okay, any congratulations that you achieved your first regret band.
I have a question. Is this constancy global? Does it depend on any parameters given here?
Yeah, this is a global. It's like, I don't know, you can probably take it to be like 3 or something. But if I thought about putting this on the homework, but it's a little like maybe too little for homework. Is to actually like see how to go from here to here. But yeah, it's an interesting exercise for sure. It's like, I didn't feel like it was worth going into lecture because it's calculations, and I'm not so good at doing them, so I probably messed them up, and maybe less illuminating to just see me struggle through them. But it is somewhat interesting. So if you have the time, it could be worth working it out. Any other questions?
Is there an intuition for what the C corresponds to, like in the problem?
I mean, the C itself is not that interesting. I think it ends up being something like, if you take, okay, maybe this is a,
or like what this root T corresponds to, like.
Which one? The square root of T?
Is there an intuition for where that comes from in the regret?
Yeah, so I think the C is less interesting. The square root of T is interesting because that is sort of I guess you can write this as sort of O of T to the minus 1/2. So this is the sort of dominant factor in the regret bound. So that is interesting, and I think the main source of it is basically this Chernoff bound. So it basically is because of the the degree of decay in the probability of the mean being far from the average. That's sort of the key thing that we need to control in this problem, is to explore for long enough so that we can with high probability know which the best arm is. So basically the square root comes from this Chernoff bound. And yeah, so I guess if we if instead of the sub-Gaussian condition we put some weaker condition, they would probably make the, you might still be able to write down a regret band, but it would probably be slightly worse. You would have to explore for a longer time for like more heavy tail distributions to have a high probability of guessing the arm correctly. Does it give you a heuristic of?
Yeah, it gives me some sense.
Do you have a good reference for looking up things in the class of the Chernoff bound, like basically perusing for bounds to work with as ingredients in these kinds of proofs?
Yeah, there's actually a handy Wikipedia page called List of Concentration Bounds, I think. And it basically gives a long list of like different different concentration bounds one can get based on different conditions in a distribution. Maybe I can link it here. I guess it's called concentration inequality. And yeah, Wikipedia lists a few. Yeah, no, the Chernoff bound is one of them. Yes. So yeah, we're at time, and as usual, we can stick around for a few minutes for any questions about anything more open-ended or anything that came up so far in the course. Thank you. Bye.
A small question about the week 1 exercises. Well, I guess this will be true for all the questions. But can you say, like, what would you say are the main takeaways from the week 1 questions? So, for example, the question on polytopes.
Yeah.
It was the main purpose of that just to get us used to the definitions, or does actually thinking about them as polytopes help in the future?
Yeah, that's a good question. I think probably the main purpose was just to give you some practice with the definitions in a sort of what I thought was a fun way, because I like geometry, so I think it's fun to work at some of the geometry. I think it is important to understand that these are polytopes in the sense that they have a convex structure, so that you can mix environments, you can take convex combinations of environments. And because we're restricted to the finite ones, I guess you can think of like finite convex spaces are like finite in the sense of like they're specified by a finite amount of, I guess a convex space in a finite set of points is like a polytope. So, and then the specific shape of them, I guess, yeah, just the idea was that, there are these relationships between the different, the more time steps you include, the kind of more structure you get. And then there are these relationships between the longer time scales project down to the shorter ones where, just forget about the last time step, for example. And then I guess it was, for the question 2, I think it is useful, I guess, in order just to see what the right convex structure is, the poly distributions, I think, is a useful way of seeing that, because on the partial map side, it's not entirely clear how to define the convex structure itself. because we saw the sort of collapsing map from the entire maps to the partial maps is not linear. So the so the convex structure, it really comes from the kind of mixing at the beginning of time, and that's captured better with the poly distributions. And then I think it's useful to understand that you can take a random deterministic environment, for example, and that gives you a stochastic environment, and you can in fact get every stochastic environment in this way. So that's why we showed that there was a surjective map from distributions on deterministic environments to stochastic ones, but it's not an injective map, so you can actually get the same stochastic environments by mixing different deterministic environments. So those are, I guess, good sort of high-level things to understand about how deterministic and stochastic environments relate to each other. I think those are the ideas behind this question.
So based on this lecture, anytime learning is looking pretty different from, what would you call it, just non-anytime learning. Is there a standard way that you would take a learning algorithm like this and try to turn it into an anytime algorithm?
Excellent question. And if you want an answer to that, I'd recommend question 3 on the homework. This week.
Cool.
But the answer is yes. Like, I guess for bandits specifically, you can basically always convert non-anytime algorithm into an anytime. For more complicated classes of environments, it might not be so straightforward, but bandits are simple enough that you can pretty much always do that.
Do you generally assume that we know delta before we have to set a policy?
Yeah, so okay, that is a very good question, because assuming, because when we pick M here, the amount of time we explore for, this time depends both on the time horizon but also on delta. So I guess knowing the time horizon is maybe fine, because you can you either know how long you're going to be playing this game, or even if you don't know it, as the Koshin just asked, there's a way to convert a non-anytime into an anytime. But knowing delta, that's not really reasonable. How would you know ahead of time, like, how big the gap between the two arms are? So that is a good point, and that is one fairly big drawback of this algorithm. And I guess one thing I plan to touch on next week is, okay, how can we upgrade this algorithm into something better, which doesn't have these drawbacks? But actually, I think I was planning to put a question on the next week's homework, where you can show how to still rescue this algorithm and turn it into something that doesn't depend on delta, but actually has a worse regret bound, but still learns the hypothesis class. So that is a good point. That it's definitely a drawback of this method, that we have a dependence on delta, which is it's a big assumption. So actually, maybe it's such a big assumption that I guess I didn't quite say that. Like, we cannot really say that. The best we can say here is that etc sub m learns the hypothesis class of, well, okay, so for Bernoulli bandits, the delta is always bounded by 1, because the reward it must be, it's between 0 and 1. So I guess this is fine. But if we want to restrict to all of the sub-Gaussian ones, we have to add, like, with delta less or equal to 1, for example. So we have to put a bound on there to to say that this algorithm learns, and then we look into more of like how to remove that dependence. That is a good point that I was kind of sweeping under the rug for now. All right, I guess we're 10 minutes over, so stop the recording and can continue next week.
Thanks, Jürgen.